will be speaking afterwards. It's my pleasure to now introduce Professor Ingo Scholtes from University of Würzburg. He holds the chair for machine learning for complex networks at the CAIDAS AI Center there. He's internationally recognized for his work on network science and temporal networks. And in his research, he's combining AI, graph learning, and complex systems. I hope that's all correct. And he has a special focus on understanding how interactions and information evolve over time in biological, social, and technical systems. The talk is entitled Deep Graph Learning for Temporal Data. Please give a warm hand to Professor Ingo Scholtes.
All right, thank you very much for this kind introduction. It's a real pleasure and an honor to be able to speak here today a little bit about our recent works on deep learning for temporal graph data. So, as was already said in the introduction, I'm heading the chair of machine learning for complex networks, but since this is the BAIOSPHERE session, I think it is also in order to say that I'm also the vice spokesperson. The vice spokesperson of the CAIDAS, which is the AI and Data Science Research Center at University of Würzburg. So here you see some of the PIs. Many of them are actually among these 130 professors that have been recently established across Bavaria. We have been founded about 4 years ago, and I think we are making good progress. So what are we talking about today? So first of all, we can think about what these different kinds of systems have in common. Like, for instance, these are cells in a tissue section. These are actors in a social network or a social organization. These are molecules in a many-body simulation in physics, or this is actually the railway network of Switzerland, which is an example for a large-scale infrastructure system. Well, what these systems have in common is, first of all, these are all systems that we are studying in different projects with different disciplines, including medicine, physics, or civil engineering, and also with software companies, but they also have something else in common. They are all examples for complex systems that consist of many interacting elements. And that's actually a very interesting type of system that we would also like to better understand using data science and also AI. So how do we often do this? Well, the nice thing is that we can, because they consist of interacting elements, we can actually represent them as complex networks by using a so-called graph or network abstraction, where the individual elements or components are represented by nodes that are connected by links. So you see, that gives us a universal abstraction, a universal mathematical formulation that we can use to understand how these systems work and how they basically, collective dynamics actually emerges in these systems. So now I don't have time to introduce in a lengthy way graph learning and deep graph learning methods, but I still think it's good to have one slide to bring everyone on the same page. So how can we apply deep learning to such graph-structured data? Well, one common approach these days is with so-called graph neural networks, which are essentially a neural network architecture specifically for graph-structured data that uses the graph topology as kind of an inductive bias by using the graph topology in something that we call neural message passing. So different from a standard feed-forward neural network architecture where all of the neurons are interconnected to each other, what we're basically using is we're using the graph topology to exchange messages between neurons between the different levels of the architecture. So that means in every step, we can only exchange messages with the neighbors. So, and then actually with some additional components, like for instance, a differentiable function with some learnable parameters, so that is what we are eventually going to train. Then a neighbor aggregation function that tells us how we aggregate information from the neighbors in the graph, and an additional nonlinear activation function, we get something that we call a graph neural network, and there's different variants of that. So this allows us to do basically end-to-end graph representation learning. So using a differentiable loss function, then we can do the standard thing like in deep neural networks. So that means if we compute partial derivatives with respect to this loss function, that gives us gradients that allow us to minimize these parameters. And then using GPU accelerated algorithms that allows us to learn useful vector space representations of graphs. Like for instance, you see now that the nodes in the different clusters in this graph here are now put into different areas of the representation space. And that allows us to do downstream learning tasks. Now, graph neural networks have been very successful in recent years in different areas, like in for instance, single-cell data where we can do cell type prediction, molecular networks, or also social networks or large-scale infrastructure systems. But I'm here to break some bad news for you, because in many cases, they are actually not working that great for data that we have often available in different scientific settings. Because the problem is that often we not only have data that tells us something about the topology of the interactions, that means who is connected to whom, but also about the timing and the temporal ordering of these interactions. So here's an example where we have a time series data set. So here time goes from top to bottom with a sequence of time-stamped interactions. So that is something that we often have in biological settings, often in social networks, but also in technical infrastructures. Think about dynamic train connections, which influence which trains you can take in what order. So we can actually represent this with a so-called temporal graph, where edges have additional timestamps. And what we can always do is we can just aggregate along the time axis, and then we get a graph again. So maybe it's interesting to think about why we are studying a graph model in the first place. Well, it's not so much about the links, it's about the path in a graph. Because if you have a graph like this, where A is connected to B and B is connected to C, we actually use this as a model because it tells us that A can in some way causally influence node C via a path via node B. Right? So that means some influence can spread in a social network or in the network of cells. The problem with temporal networks is now we additionally have this time dimension, and that means we have to consider what we call time-respecting or causal path. So that means a path is only time-respecting if the sequence of links happens in the right chronological order. Like in this example, where we first have the interaction from A to B and then from B to C, some causal influence can spread from A via B to C, but you see, we can change the temporal ordering of the interactions without changing anything about the topology, and with this, we can break this time-respecting path. So now, if the interaction BC happens before AB, there's no way that A can causally influence C via B, because that influence would have to travel backwards through time. And that's a problem, because the arrow of time restricts what can be causal in the universe. So we call this the causal topology of temporal graphs. It's essentially the set of all time-respecting paths between all pairs of nodes in a temporal graph, and that is basically the necessary condition for causal influence in a complex system. So the important message here is to see that even without changing who's connected to whom, just by changing the temporal ordering, that changes the causal topology of a system, and we could show in the last years that that has massive implications for real-world systems. Thinking about how dynamical processes spread, like diffusion or epidemic spreading, the centrality of actors in social networks, the controllability of systems, and also in terms of graph learning. Okay, so the important message is causality in temporal networks basically lives in the order of the events and not just in their topology. And the problem with common graph learning techniques, and also actually temporal graph learning techniques, is that they are really insensitive to this dimension, because they are doing something that we call time window batching. So that means within certain time windows, all of the interactions are batched or aggregated, and then the learning algorithms apply to that. And that ignores the microscopic temporal ordering of the interactions, and thus these kind of time-respecting paths. So and this is actually a problem not only for standard GNNs that do not have a notion of time, but also for many state-of-the-art temporal variations of GNNs that do not actually see this. Okay, so now what can we do about this? In network science, since a couple of years, there have been ideas around where we can use what we call causality-aware or causality-preserving representations of temporal graphs. So the idea is, for instance, we could encode the causal structure of a temporal graph in terms of a directed acyclic graph by using these kind of event graphs. That is essentially a line graph transformation where every timestamp interaction becomes now a node, and an edge exists if there is a time-respecting path that follows the arrow of time. So that is nice because that fully encodes the causal topology of the graph. The problem with this representation is it can be really huge, because if you have 10 million timestamped interactions, which is not uncommon for large scientific data sets, then you also have a graph that has millions of nodes and links, and that makes learning really hard, and also you need a lot of training data and you need a lot of resources. Okay, so what did we do about it? Well, we kind of reconsidered why we are using time-aggregated graph representations. The main focus is that they are compact, right? Because we are aggregating all of the interactions happening at a certain time in only a single edge, and that's why this representation is actually very compact. But at the same time, we have the problem that you see this representation is insensitive to this kind of causality structure because the ordering does not affect it. So what we came up with is we developed a new representation which we call kth-order de Bruijn graphs, and the idea is actually very simple. We generalize graph representations by turning all of the edges in the graph into nodes, like the edge from A to B now becomes a node AB, and that gives us a space where we can represent time-respecting path of length 2. So this is actually a simple idea because a standard graph model that we're using in graph learning represents edges which are path of length 1, and we're doing the same but with path of length 2. And we can obviously generalize this to longer path as well. So you now see we get also a compact representation, but that compact representation is now sensitive to the error of time. You see, for instance, this kind of causal influence disappears if we just change the order of the events, and we still have this kind of static compact representation. So we call this kth-order de Bruijn graphs, so that means the nodes are kind of time-respecting path of length k minus 1 for a general k. Edges represent the causal structure, and it's actually a timestamps aggregated, so that means it's a compact encoding of the causal topology, but it also has some loss because we can only encode correlations up to length k, so that means we have to decide what kind of fidelity in the representation we want actually for certain data. So this is great because we can not only use it for temporal graph learning, but in recent years we have shown that we can also use it to analytically study dynamical processes in complex dynamic networks. We can also generalize a very well-known concept in graph learning, graph Laplacians, to these kind of higher order Laplacians, which then actually allows us to define higher order graph convolutions that can also be the basis for graph learning. Okay, so how do we do this? I don't have much time, so I can just give you one slide overview. So the first thing that we have done is we have actually generalized some works on expressivity of GNNs to these temporal event graphs. And this is actually very nice because what we basically do is we define a neural message passing scheme on such an event graph that then forces that the messages that flow through the neural network, they have to follow the arrow of time, and they cannot violate causality. And by this, the representations that the network learns, they capture these kind of temporal patterns that are expressed in the causal topology. So that means we can do this, we get from this a causality-aware temporal GNN. And the nice thing is also this has provable expressivity because we know exactly what notion of a temporal graph isomorphism this temporal GNN architecture can distinguish. So that means in that sense it's also a nice generalization of, for instance, works that Stephanie has done on graph isomorphism networks. So if we apply this to real data, we can also make synthetic experiments where we actually tune graphs in such a way that the only thing that differs is the causal structure, and our architecture is able to reliably distinguish that, while other temporal GNN architectures fail because they're blind to this important aspect. Okay, so the problem is this is not very efficient for large data sets, so we have actually generalized it to these de Bruijn graph models, which are more compact. And this is another causality-aware graph learning architecture where we now basically apply neural message passing to these higher order representations. And that again forces the messages to follow the arrow of time and the way in which causal influence can spread in the system. That again gives us causality-aware representations of nodes, and that massively improves the performance of GNNs in time series data. For instance, we have applied this to node classification and also node regression, and we can see that we beat baseline temporal graph learning methods by up to 18%, which is a large margin for these kind of benchmarks. You can find more details there. All right, so we also turned that into software. So we have an open source library, PathPyG, out, which is a PyTorch-based library that basically facilitates causality-aware temporal graph learning. That means all of these models are implemented on the GPU. So I also have one nice illustration of this. Unfortunately, I can't show you the dynamic visualization of the temporal graph because that computer doesn't have internet, but you get the idea. What we have here is basically a static representation of a temporal graph, and we have colored the nodes here based on some clusters that we have encoded in the temporal ordering. And the temporal ordering is such that something that is moving through the network will always stay within these clusters that have actually these colors. If we apply standard graph learning techniques, we get a representation of the nodes where we cannot distinguish these clusters because the network is blind to this kind of pattern in the causal topology. If we apply our method, you see that we nicely separate that. So that's an illustration of the kind of pattern that we can actually learn. We also have recently, this reminded me about the work by Daniel with this kind of risk score. So we recently also applied this temporal graph learning to software analytics in a collaboration with industry partners, DATEV and Honda Research in Offenbach and in Nuremberg. The idea is that we can analyze dynamic developer collaboration networks based on software repository data, and then actually find signatures in the collaboration patterns that actually turn into risks for the project. So we have developed a platform that allows stakeholders to assess these kind of socio-technical risk factors in open source communities, which is these days a really important concern in terms of software supply chains. And with this, thanks a lot for your attention. If you want to learn more, you can find me in the Speakers Corner.